Welcome to the lecture X-ray Absorption and Emission Spectroscopy. My name is Thomas Kroll from SLAC National Accelerator Laboratory, and in this lecture we will go over the basic principles and applications of non-resonant and resonant X-ray emission spectroscopy. If you later have any questions, this is my email where you can always reach me and ask. So the principle is always the same. We have a photon in and a photon out experiment, meaning you come in with a photon into a sample, and depending on the energy, you excite an electron from the 1s orbital into the vacuum, which is different than what you have dealt with before, where you excite an unoccupied orbital like a 3D or 4p. In the non-resonant case, you ionize the sample, so you're left with the 1s hole, which then gets filled successively either with an electron from a 2p core level, with a 3p core level, or a filled orbital in the valence region. And these then give, depending on where you decay, you get K alpha, K beta, and K beta valence to core emission spectra. And here you see some examples that look very different and they have very characteristic information. And we go over them one by one later on. In order to do such an experiment, you need to be able to control the incoming photon energy as well as the outgoing photon energy. The incoming photon energy is controlled by the beamline monochromator, and the outgoing energy is selected by a set of analyzer crystals, where the selected energy depends on the angle, the break angle, and the crystal and crystal cut that is used. And in order to reach all these various emission lines, you need a bunch of crystal cuts. And we have a lot of them. This here is just like a subsection of the crystals that we have. We have quite a number. And here you see already with this subselection what emission lines you can reach. Here, for example, is K beta, iron K beta, nickel K alpha, cobalt K beta, copper K alpha, and so on and so forth. They're all there. So basically, for whatever element you're interested in the periodic table, we will have a crystal that can help you. And such experiments could be done at SSRL until recent at beamline 6.2 in the middle hatch. We now built a new beamline and moved our spectrometer over. Its name is 15.2. Where we have all the spectrometers available that were at 6.2. So mainly the XAS and the RIXS spectrometer, the Raman spectrometers, and all capabilities that were there are also beamline 15.2. So nothing has changed in that regard. However, there are a number of new capabilities that we have at beamline 15.2. Which is mainly connected to the fact that we can now focus the beam down to a very small size. We can also make it larger, but we can focus it down to like 5 by 35 microns or even less, which then enables experiments such as high pressure experiments or pump probe experiments for which we bought a laser. Now we have a laser that can be coupled to the camshaft of SSRL and do pump probe experiments. So that's all there. And the new beamline is 15.2, and it should be available now for users after we're done commissioning it, which is ongoing, and it should be available like in January 2021, we think. Okay, with that, let's come to the outline of this presentation here, of this little lecture. I want to talk about mainly three parts. One is non-resonant X-ray emission. So we have a fixed monochromator and a scanning spectrometer. Then we get K alpha, K beta, and then it's the core spectra. We can have high resolution X-ray absorption or HERFD, where we scan now the mono and we keep the spectrometer fixed. And the third one is a combination of both. We scan both the mono and the spectrometer, and we get resonant inelastic X-ray scattering. And the fourth one, which I'm not going over here, is X-ray Raman spectroscopy, which we can do. Now we scan the mono and we keep the spectrometer fixed, and we detect the energy loss, which means we can, using hard X-rays, we can measure kind of soft X-ray, usually soft X-ray regime spectra like the carbon K edge, oxygen K edge, transition metal L edges, these kind of things. So let's start with number one, XA non-resonant X-ray emission spectroscopy. So remember, we have a fixed monochromator set above the absorption energy, and now we're scanning the emission spectrometer. So to give you a little bit again on nomenclature, we excite from a 1s core level. So we excite a 1s electron out into the vacuum, which means it is a K excitation. So all numbers are with K because it's 1s shell, it's a K shell. And now it just depends from which shell you decay back into the 1s. If it's the second shell, it's called alpha. If it's the third shell, it's called beta. And if you have multiple within one shell that are like easily doable, then they're called K alpha 1, K alpha 2. Like when you decay from a 2p 3/2, it's a K alpha 1, it's a 2p 1/2, it is from the K alpha 2. Okay, so with that, let's have a look at intensities or relative intensities. The most likely decay after 1s excitation is the 2p to 1s decay, which is called K alpha, K alpha 1 and K alpha 2. The next likely one is from the 3p into the 1s, which is the K beta. However, that's around a factor of 10 or a factor of 8 less intense. So when you plot it here on the one axis, then you go from black to red, and this is the spectrum you get. Here it's blown up. And the next one is the valence to core. You know, you fill the 1s with a core electron. That is around a factor of 100 less than what you have for the K beta, so around a factor of 1,000 less than what you get for a K alpha experiment. And here, very subtle, you see like a little bump, which when you blow it up, it gives a green curve, which has actually quite some features. It is very weak, but is still full of features, and you can actually measure them. So that's a very good finding. So then let's go and see what all this means. Let's start with K alpha. The K alpha is, as I said, the decay of the 2p into the 1s, which leaves the 2p whole, which has an L equals 1 and S equals 1/2. So you have spin orbit coupling of 3/2 and 1/2, which is strong. So actually L and S aren't good quantum numbers anymore, but J is 3/2 and 1/2. So we are in the JJ coupling regime, which means we talk about two energy regions, one with a J equals 3/2, which is K alpha 1, and one with J equals 1/2, which is the K alpha 2. And they're split by 3/2 spin orbit coupling. This is manganese, so that's like 6 eV is a spin orbit coupling, so around 9, 10 EVs or so, maybe it's 7 EVs is the difference between the K alpha 1 and the K alpha 2. And the shape of these, which gives you the final states, which are the vertical sticks, or the transitions into final states, is now given by the interaction of the 2p hole with the 3d electrons, or with the valence electrons. So that gives you the shape of the whole thing. And the position is given by the oxidation state. So when you look at it in a little more detail, here's an example for manganese 2, manganese 4, and manganese 7, from blue to green to red. And you see that the position of the K alpha 1, it changes towards lower emission energies, while the K alpha 2 also changes, but not that much. And also the width of the K alpha 1 changes as a function of oxidation state. So there is a number of like fingerprints, but not that much. So it has not been used a lot in the past, because the K beta, which we'll talk about right now, is more sensitive. However, it is 10 times or 8 times more intense, so that has its own advantage if you have like a very dilute sample, for example. And the K beta is very sensitive to the spin, for the reason that the 3p hole that you now have has a weak spin orbit coupling. So you can stay in LS coupling, which means spin is a good quantum number. And so you can easily model your system. And so we get two main regions. It's called K-beta 1,3 and so-called K-beta primed area. Again, you have two features, two main features, same as in K-alpha, but the origin is completely different. And that is because in K-alpha, it was given by the spin-orbit coupling, the strong spin-orbit coupling. Here it's weak. And here the dominant factor is the 3p and 3d exchange interaction. And what that means is you have, let's go to here, you have a hole in the 3p. I omit all the two other orbitals which are completely filled. And they interact with the 3d electrons, which is this manganese chloride, is a cubic environment, D5 high spin. So you have 5 spin up electrons. And if the 3p electron is parallel, the spin of 3p is parallel, that is one configuration. The other one is when it's antiparallel to the 3ds. And they have a different energy. And the energy leads to for the parallel case, leads to a higher emission energy, which is then the K-beta 1,3, and the K-beta primed is at a lower emission energy, and that is when the spins of the 3p and the 3d are antiparallel to each other. And you also have kind of like an intermediate case where you can actually flip a spin in the 3d, and that has intermediate energy, and that is where the shoulder comes from. So what we learn from that is that these two features originate from the 3p interacting with the spin of the 3d. Now, if you think about another system, let's say an iron or manganese, whatever, it's D6 low spin, so the T2G orbitals are completely filled, the EG orbital is empty, which means their spin equals 0. In that case, it wouldn't matter if the 3p is spin up or spin down, because it's coupled with spin equals 0. So that gives you the same energy. So we would expect that this peak here, the weak one, will go down. It will go away actually with intensity, with decreasing spin. And that is exactly what we observe. So when we look here at the K-beta primed, and you look at the red curve, that's a singlet, S equals 0, then this K-beta primed is gone. And with increasing spin, it goes up, goes to green, like a little up. It's hard to see for the solid blue one, and to green, to red, and to blue dashed. And also, what's important is the center of mass stays constant, because it's a core-to-core emission process. And so the center of mass is the same. So this here goes down intensity. That means that the position of this main peak goes towards lower energies, or the other way around. When you go to a higher spin states, the K-beta 1,3 goes towards higher energies. So there are very characteristic features in the K-beta spectra, which has made it so nice to look at the spin. And remember that spin and oxidation state is coupled. If you change the oxidation state, you will change the spin. And so you're sensitive to both. And there are a number of ways to actually look at the data without having to do like some hardcore theory. Just taking your data and look at it. And one is the so-called integrated absolute difference, IAD. What you take is you have a reference spectrum. In this case, it's a cobalt low spin, D6. And you compare it to your data. You subtract it, you take your data, you subtract the reference spectrum, which gives you a different spectrum as it is shown here in the bottom of this left figure. And then you take the absolute value of the difference and you integrate it, which gives you a number. And that number is proportional to the spin. So here for the reference minus reference, that's 0, because it's the same thing. They took a reference data at like S equals 2, and everything in between is on a pretty much linear relationship, which means you can easily determine from this value, this IAD value, the spin of your system. And it's been done here for lanthanum cobalt oxide, which is at D6 low spin at low temperatures, and you mix high spin components in it with increasing temperature. And that has been done here by George Wanko and his friends with a varies the temperature to measure the K beta, as is shown here for a number of temperatures, and then plots the ID value that they then couple to the spin. And they see it goes up to a spin equals 1, which is the effective spin of that system. Another way is to look at the first moment. So the first moment, as is defined here, is the same as the center of mass. And when you look here again at K beta of a number of different manganese complexes, manganese fluoride complexes, then the spin varies for all four. And as I said before, since the center of mass of the whole system, of the whole spectrum stays the same, when this peak here, the K beta prime, goes down, the K beta 1,3 has to move to lower energies. And actually, that's exactly what they observe. You can read it here in this review article. That was a change in spin. You change the position of the first moment of a range. So here they took, I don't know exactly, from 6,485 up to 6,500. And now when this first peak moves, the center of mass will move, and it's a linear relationship. And that is actually pretty sensitive. They have used that for the photosystem 2 system. That's here Johannes Messinger's paper. So in photosystem 2, it has 4 manganese in its active center, in its cluster. And upon illuminating it with light, it changes its oxidation by 1. So one of the 4 manganese changes oxidation upon each of the flashes. It's shown here in the cork circle. And when you now take the data after various flashes, you see it here. The difference is super small. It's super small, but it's there. And when you take now the first moment and you plot the first moment versus the flash number, then you see a clear difference. And this is actually what you expect also in terms of oxidation. And remember that the oxidation is coupled to the spin. You sense it to the spin, but the oxidation and spin are coupled because if you take one electron away, you automatically change the spin, and hence you're sensitive to oxidation. It's also super powerful when you look at pump probe experiments. This year is an experiment done by Wen-Kai Zhang some years ago. And what they did is they used iron trispyridine. It's a D6 low spin ground state, and when you excite at a given wavelength, you excite a metal ligand charge transfer into a metal ligand charge transfer state, which then decays into a high spin final state. It's quite long-lived. And the big question is, how does it get there? Does it get there directly, or does it get there by an intermediate step where it is an intermediate spin for a certain amount of time? And from there, it can then easily decay into the high spin. And so they did the experiment at LCLS. Again, they looked at different spectra. So the reference is the ground state, D6 low spin. And this is reference of the data minus the ground state. Red is up, blue is negative. And here you show some reference complexes. Red is a quintet minus a singlet, blue is a triplet minus a singlet, and green is a doublet minus a singlet. And when you look at the various parts, then you see at this energy, all of them are positive with different intensities, but all of them are positive. At the higher energy side, at the lower energy side, nothing really happens besides for the quintet. But the biggest difference is here in this energy range, like in the intermediate energy, let's say, where the triplet has a positive signal in the different spectrum, while the quintet has a negative signal. And so when you choose these energies and you do the cuts here, A and B in this case, then you get these type of curves that you can fit them with a kinetic model. And what you found is that actually, yes, you need a transient state, which is a triplet intermediate state. So that shows you that K beta is a pretty powerful method. Again, its characteristic changes upon variation of the effective spin, which means it is sensitive to oxidation. It is even sensitive to covalency in some cases minimum. you can imagine if you take a D5 high spin and then you switch on covalent mixing with the ligands, the only thing that can happen is that the effective spin goes down, which means it changes your K-beta spectrum, and you directly have a measure of covalency. As a little warning, you should also be a little careful, because for at least for low-spin spectra, they're also affected by the crystal field, and so there you need to be like a little careful of what you say and how you do your analysis. So then the third option for a reasonable decay is from the valence into the 1s. The big advantage for the valence to the 1s is that you're now probing the occupied valence orbitals, like those that participate in chemical bonding. So you can expect a very high chemical sensitivity. Of course, you pay a price. It is like 80 to 100 times less intense than the main line, which is again around 10% or 10 times less intense than the K-alpha line, which means the K-beta valence to core is like 1,000 times less intense than the K-alpha. But it contains a lot of information. And so let's go over it. Let's first think about what we do. So we excite a 1s into the vacuum, and the 1s gets filled by a valence electron. So in the final state, we have a hole in the valence, which is exactly the same final state configuration that you can reach in a photoemission experiment. And so that has been done for some iron complex. And photoemission experiments are very well understood. And we know that here at like 20-something EV, that's oxygen to S for this complex. That's the binding energy of the oxygen to S. The main peak here is the iron D5 and ligand, and it's oxygen to P, so it has a lot of ligand character. And then the iron D4 is here. Now, when we look at the K-beta valence to core spectrum, we see a feature at the same emission energy relative as O2S. So we can assume this is actually where it comes from. It has mostly oxygen to S character. The main peak here mostly has ligand character. We don't see anything from this 4P, from the iron 3D4. And that is because that is a decay from the 3D into the 1s, which is a quadrupole, which is not dipole allowed, and hence it's very weak, and we don't see it here. Now then, to test if in valence to core the K-beta double primed is really given by the binding energy of the ligand, they did the experiment, or the part of the experiment, where they just changed the ligand, you have fluoride, oxygen, nitrogen, and indeed they follow exactly what you would expect from binding energies. The other thought is, like, if this is really given by the ligand, but we're still probing at the metal center, then we can only see it the more they talk to each other, the stronger the mixing is. And so that has been done then, was been tested by varying the manganese oxygen distance by using complexes as like various distances. And then you look at the relative intensity. And indeed, what they found here, the further away the ligands are from the manganese, meaning the less ligand mixing there is, the weaker the whole features and the whole spectrum. So that means that we can summarize that we reach the same final states as in like valence band photoemission. That gives us an idea of how to look at the data. And we know that the valence to core is sensitive to the ligand character and the ligand mixing. All right. And you can also quite easily actually simulate these using DFT method. This here now are spectra that have differences in like in the ligand again, and you see very clearly differences in where the K-beta double primed is. You see very clear differences in the K-beta 2,5 region, and they're actually relatively easy to simulate. This here now is for the red case, the chloride case. This has been done using Orca. You see the reference. Look at it. It's a very nice paper. And you can also then, that gives you the opportunity to look at the orbitals. And what you find is that the double primed is indeed the ligand 2s orbitals. And you're mostly sensitive here to the ligands rather than the metal ion, but the ligands that mix into the metal. And potentially this is a very powerful method because it is very sensitive even to very small changes. So these are calculated spectra when you have an iron 4 hydroxy compared to iron 4 oxo complex. So the only thing is you take a proton away. You do nothing else but taking one proton away, but the change in the spectra is quite significant, in particular here in the Kavita double primed. And so it is super sensitive to the ligand character, and it also allows even for small variations, such as like taking a proton away. Okay, with that, let's come then to the next one. Let's go to high resolution X-ray absorption spectroscopy. So now we scan the monochromator and keep the spectrometer fixed. So exactly opposite of what we have done before. So the way you normally do an experiment when you do it's like a germanium detector without any analyzer crystal. Then you get a spectrum like this, let's say. You have the elastic scattering in there. You have a Compton scattering and some other crap. And of course you have your signal. But the germanium detector has like 200 eV energy resolution. So there's no way you can distinguish between like alpha 1 and alpha 2. So what you do is you select a broad energy window in order to avoid all this intensity here, but it still gives you strong background and broad spectra. So here I give an example. This is iron 3 TPP bismuthazole, the KH. This is a D5 low spin. It has one hole in the T2G and 4 holes in the EGs, and the T2G should be somewhere here. And if you have some fantasy, then you can see here the T2G. When we now put in our emission spectrometer, where we can distinguish between K alpha 1 and K alpha 2, and we have an energy resolution of below an EV, then everything that we windowed out before now is this whole spectrum. And out of this spectrum, we set our energy, or that be the one that we detect, our spectrometer, to this energy region here. So we gain a lot in energy resolution. And when you now take the data, you see here very clearly the T2G peak. The price you pay is you lose intensity. However, this here is a very sloppy data that I took some time ago. That was done very fast. If you just measure it a little longer, it will be super smooth. But even with that data quality, you see very, very clearly the T2G peak here. So you have basically no background. I compared the background here, it's at 0. Because we have 1 EV resolution, we're not sensitive to anything outside that energy. And you can resolve, you get very sharp spectra. And this background actually is a very important point here. So this is a slide by the courtesy of Graham George, where he shows data, normal XAS data using a germanium detector compared to HERFD. I didn't say that yet. So HERFD is exactly what we do here. That's high energy resolution fluorescence detection. That's what it stands for. And this is some selenide complex. That's these are from the same sample. It's a 5 micromolar selenium complex. And it's pretty hard to see here because of all this huge background. You have huge background with teeny tiny broad signal. When you do HERFD, you get rid of all the background. And suddenly the signal is huge and it's sharp. And so that is the difference. And because you get rid of the background, you can measure easily very dilute samples. The lowest I got is like 100 nanomolar so far. So that's all doable. That's a big advantage of of HERFD. And here's like a little example where it has been used. It is for a platinum at 3 edge. Here on the left, again, you see the difference between total fluorescence in the germanium detector and the L-alpha-1 emission. And yeah, no comparison between black and red. Black is super broad. Red gives you a chance to see something. And so what they did here is, you can see it in this paper by Merte. They varied the potential, and then it goes from metallic to oxide character, and that is like on the order. So this here is 2 eV. It's like a little bit more than 1 eV, and you can very clearly see it. It's very clearly resolved, which is impossible when you're using total fluorescence. All right, so this is that's HERFD. So then let's go to combination of both resonant inelastic X-ray scattering, RIXS, or also the resonant X-ray emission spectroscopy, like RIXS. It's a little hard to pronounce though. So the way this works is a combination of both. So first, let's assume we have, let's say iron D5 in low spin. So the 1s is fully occupied in the ground state. The 2p is fully occupied in the ground state. And you have one hole in the T2G in the valence electrons in the 3D. So you can do a soft X-ray experiment where you excite from the 2p into the 3D. That's around 700 electron volts, and you end up with a final state that has a 2p hole. And now, for example, here the T2G is filled, or the EG. And that gives rise to spectra that look like this here. It's for ferricyanide as well as for ferric tag N in blue, with a natural line width of like 0.3 electron volts. And you see a lot of features very clearly distinguishable, these two. Yeah, it's great. However, it's soft X-rays, which has its own issues, mainly given the vacuum that's needed. So we have another option if we want to use hard X-rays. You can excite from the 1s into the 3D, which is the same as what you have done all this week. So you excite from the 1s into the 3D, which now at energy, you need like 7 keV for that. Now we have a hole in the 1s, and the additional electron is here, for example, in the T2G. So that's an intermediate state. Or if you just think about the KH, that's the final state there, and you get spectra that look like this. Very broad, hardly to see anything, particularly compared to this one. And that is because the natural line width for iron is like 1.2 eV or so. But life isn't over yet. It still goes on. So the 1s, as we said before, it wants to get filled. It's an excited state. And it gets filled, first of all, with an electron from 2p. So the 2p decays into the 1s, which gives us to a configuration where we now have a hole in the 2p. And if you see that, this is exactly the same final state configuration that you get for an LH. So we expect kind of LH data, but with hard X-rays, because the transition here from 2p to 1s, again, is in hard X-rays. And when you take the data, what you do is you have two options to take the data. One is you can scan the first you sit at a photon energy, so you excite into a given orbital, and then you scan the emission energy like one by one, and you go here and you scan in this direction. Or the other option is you set your spectrometer to a given energy transfer in this case, so a given emission energy, and then you scan the photon energy, and then one by one you build the whole map, which is now a 2D map, which means when you integrate it in the vertical direction, you get the KH again. But if you integrate it in the direction of the photon energy and you exclude the parts where we go into the 4P, you get an LH-like spectrum. I come in a second to what all these features mean. And actually here it is, second's already over. So this here is a ferricyanide data. It's a D5 low spin. So here it's 5 d electrons and a hole in the ground state in the T2G. So when we set our incoming photon energy to this energy here, then we excite from the 1s into the T2G. And this state will decay. The 2p will go into the 1s, which means we are checking up this energy direction here. Which means when we get two features here, the L3 and the L2 like features, or K alpha 1, K alpha 2 in the resonance case. And these here are then the features for the EG. When you excite from 1s into the EGs, it's these two features. And you see how super well they're separated and visible. And what's now very interesting is that for ferricyanide, the T2G excitation, it has exactly one final state. So what we can do is we can do a cut here through the T2G and plot it on top of an LH spectrum. Now, red is the cut and blue is the LH spectrum. And you see that they have the same width. So the very cool thing is that we're not experimental energy evolution limited if you don't screw up your setup, of course. We're only limited by the 2p Kroll lifetime. So that is a very exciting result, which means we now have with RIXS the opportunity to get very sharp data with with an LH-like information. And since I talked about cuts, there's a various numbers of cuts that you can do. So first of all, you have clear separation of features in the 2D plane. So this here is a simulation for iron 2 plus high spin. That was cobalt. No, that's iron. Iron 2 plus high spin. And I told you already, you have the opportunity to do a vertical cut, constant emission energy, which is an LH-like, because an energy transfer, which is a difference between the incident and the emitted photon energy. You also have the opportunity to get a diagonal cut, which is a constant emission energy cut, which is actually the same as HERFD. So that means here, that's the same as if you put your emission spectrometer at one given energy and you scan the incident energy, and you have a diagonal cut. And here you see the issue with that one. While it gives you, or the potential issue, while it gives you a very high resolution, you might have difficulties with relative intensities. So here you see there are a bunch of different features for the iron 2 plus high spin, which is D6 high spin. And when you do the cut here along the black curve, you miss the maximum of this feature, and you totally miss the maximum of this feature. Now, when you move slightly over, you, for example, go through this one, but you miss the maximum of this one. So there is care that you need to take how you then interpret your data and how you compare data too. Another step of interpreting data is one, taking this RIXS data is very good because we get a clear separation of spectral features in the 2D plane. For example, here on the right, as I say, that's the ferric TechN, D5 low spin, we have the T2G and the EG. So they're super well separated. And I compare them here with the HERFD spectrum, which is a diagonal cut in blue. They're still pretty well separated, to a direct KH, where they're not that very well visible. Another thing is when you take diagonal cuts, look at the one on the left. That's also TechN. It's iron 2 plus, D6 low spin. For the KH, we expect exactly one peak because there's only one absorption energy that you can reach. However, there are multiple emission energies, as you see here when you look at the diagonal. So there's like a bump here, and at higher energy transfers another one. Now, when you do a diagonal cut, you go through this main bump, and you go through the tails of the next one. And so if you look at it here in the blue curve, this is asymmetric. So you could have the idea, okay, I need to fit in one curve here and another peak here and start interpreting something showing up. And again here, be careful. This one here is not a real feature in the HERFD because you do a diagonal cut and you see the tail of the higher energy transfer feature. So be aware of that. Then let me quickly say something to what you can use it for, what it's really good for. And here I give you an example of one of my own papers. If we look at cytochrome C, here this is oxidized cytochrome C, that's an enzyme. And we compare it to model complex, where the difference between the model complex, which is iron 3 TPP bisidazole, to the oxidized cytochrome C is one extra ligand instead of ether, which has a sulfur containing ligand. In cytochrome C, it's an imidazole, so you have a nitrogen X neighbor to the iron. So that is the main difference between the two. This is how the RIXS spectra look like. I subtracted here the rising edge and only focus on the 1s to 3d transition, which is weak because it's partipolar allowed only. And so when you do diagonal cuts, it's shown here. You see some small differences. However, when you do vertical cuts, you now can do vertical cuts at selected energies. And you compare these, and you see small but characteristic differences. And we simulated these, and we found that it's mainly a difference in the metal character along the axial direction, which makes total sense because it is the only thing that we changed. We changed the ligand mostly in the axial direction. And if I go back here, in particular, the change here in the in the L2 like edge, or K-alpha 2, in the resonant K-alpha 2, this increase in intensity when you go from the model complex to the protein or to the enzyme, then you have an increase in covalency, increase in covalent mixing, which is actually the characteristic underlying description of this feature here. We have seen that later on also in hemoglobin, actually. So yeah, this brings me to the summary. So first, X-ray absorption spectroscopy is a very powerful tool for electronic structure to characterize samples. They're like very well developed state-of-the-art instruments that you couple with third generation beamlines. We have that here at SSRL, beamline 15.2, but there also exists at a number of synchrotrons worldwide. Since it's core sensitive, it is element sensitive, and you can look at elements across per table. It's actually site sensitive, site selective. Hard X-rays, they penetrate very well, way better than soft X-rays, which means it gives you capabilities to study like difficult environments, high pressure, proteins, solutions, gas phase, everything. And with that, it also opens up the possibility for like multidisciplinary research. And then if you want to read more about it, these here are, I think these are all the papers that I've like cited in this presentation, number of review articles and specialized articles. I recommend you all reading them because they're very good and they're very, very informative. And then with that, let me acknowledge the people that we work with here at SSRL for the spectroscopy, Dimaster Sokaras, Dennis Nordlund, Dan Novak, who is now at Industry, and Alessandro Gallo, as well as absorption and XAS operations like Riti, who is the organizer of this workshop, and many others, LCLS, and then obviously get funded too. And with that, thank you so much for your attention, and I hope this helped you a bit understanding how X-ray spectroscopy works. Thank you.